The spectrum showed a bump where dimethyl sulfide should be. On Earth, that molecule comes almost exclusively from ocean microbes. Around a sub-Neptune 124 light-years away, that single overlap was enough to make K2-18b the closest thing to a biosignature anyone has recorded. The excitement moved faster than the data did. JWST's transmission spectrum of K2-18b showed an absorption feature consistent with DMS, sitting in the same wavelength region where methane also absorbs. The instrument was working near the edge of its sensitivity. The signal was real enough to publish. It wasn't strong enough to close the case. Here's the first fact worth holding on to. Detected and confirmed are not the same word. Scientists expected either a clean methane signature or nothing distinct at all. What arrived was neither. The line could be DMS. It could be methane behaving in an unexpected way. It could be a blend the current resolution just can't separate. K2-18b itself resists a single description. Its radius and mass suggest a sub-Neptune too large to be rocky and too small to be a gas giant. One model treats it as a Hycean world, a deep, warm ocean sealed beneath a thick hydrogen atmosphere, chemically capable of producing exactly the kind of sulfur compound JWST may have seen. Another model treats the interior as a magma-ocean, hot enough that no liquid water surface exists at all, with the same hydrogen envelope on top, producing similar spectral behavior. Two structures, one spectrum. The atmosphere doesn't tell us which one is real. The boring explanation deserves to be tested first. Instrument noise, stellar contamination, or a misidentified blend with methane could account for the entire signal without invoking any chemistry unique to DMS. This isn't a weak possibility. It's the default position any careful reading of the data has to survive first. The more interesting explanation is that DMS is present, and abiotic. Laboratory photochemistry in hydrogen-rich atmospheres has produced DMS without biology, and cometary ice analogues have shown the same molecule forming from ultraviolet-driven sulfur chemistry. Earth's biology isn't the only chemical pathway to this molecule. It's simply the only one nearby. The frontier explanation is the one the headlines reached for. Biological production, the same pathway that makes DMS in Earth's oceans, operating in an alien ocean under an alien sky. It remains possible. It's just not supported by anything the spectrum currently proves. The obstacle is resolution. A single transit, blended lines, and a signal near the detection floor can't tell these three explanations apart. So scientists stack more transits, tighten the wavelength coverage, and model the atmosphere against both interior structures independently. There's a second obstacle, and it's theoretical, not observational. There is no complete model yet for abiotic sulfur chemistry on hydrogen-dominated exoplanets. Without that model, a real detection of DMS can't be separated from a false positive for life. The instrument problem and the theory problem are different problems, and only one of them gets better, with more telescope time. Future observation cycles, the aerial mission, and ground-based extremely large telescopes will raise the signal-to-noise on K2-18b's atmosphere by roughly an order of magnitude. That will likely settle whether DMS is actually there. It won't settle what DMS means, because that answer depends on a theory of chemistry that doesn't exist yet. If you want to follow this story to wherever it actually lands, subscribe. The next observation cycle on K2-18b may answer one question and open three more. The temptation is to treat a near detection as an announcement. The more disciplined read is colder. The signal is exciting because it almost means life, and unsettling because almost is the most dangerous result a biosignature can produce. The honest question is which side should carry the burden of proof, the biology that needs an ocean, or the chemistry that needs no life at all?